This presentation will go over the basics of valence bond theory. First, we'll describe the formation of covalent bonds in terms of orbital overlap. We'll define and give examples of sigma and pi bonds, sigma given by lowercase Greek letter sigma, and pi given by lowercase Greek letter pi. So far, we've talked about atomic orbitals on individual atoms, but what happens to them in a bond? Our current understanding does not address that. There are two main theories about how electrons behave in bonds. We'll start by going over valence bond theory. Valence bond theory explains the behavior of electrons in shared orbitals. In other words, in covalent bonds. There are two main assumptions in valence bond theory. One, an orbital of one atom overlaps with the orbital of another atom. And two, single electrons in each orbital to combine to form an electron pair. So what does this process look like? On the right, we have a graph showing the energy versus internuclear distance. So we're talking about how far apart our nuclei are. When we form these overlapping orbitals, there is an energy associated with that bond formation. The electrons will be attracted to both nuclei. As we put the atoms in proximity with each other, the attraction of the electrons to the nuclei of the atoms makes the energy level go down. So if we start on the right-hand side of the graph and we go toward the left. But wait, I thought that energy must be conserved. You're right. Energy must be conserved. But remember that we have energy in our system and energy in the surroundings. Our system, for this purpose, is two elements coming together. When we sum it with our surroundings, we'll get no energy change. Now, by convention, we have the unbounded or the unbonded atom energy as being equal to 0. As the electrons start to be attracted to the nuclei in the other atom, as they're coming closer together, the energy level goes down. But there is also a repulsive force between the nuclei that is occurring. So we have two positive charges repelling each other. The two of these forces balance each other until we reach an energy minimum. It's a sweet spot where we get the minimal interaction between nuclei, but a maximum attraction between electrons and the nuclei. At this point, where the energy is reduced to the lowest possible value, we denote the internuclear distance here as the length of the bond. Note how the electron clouds on the hydrogen atoms are overlapping when that optimal bond distance is achieved. That is what we're talking about with overlapping orbitals making the bond. If we get the atoms closer together from there, the repulsive forces between the nuclei dominate, and that means we end up with a rapidly increasing energy. The bond energy is the distance between the separated atoms, the energy of the separated atoms, and the energy at the minimum. In this plot, it's negative 7.24 times 10 to the negative 14th joules, which seems like a really tiny amount until you multiply it by Avogadro's number. And then you get the energy for a mole of those hydrogen atoms forming, or those hydrogen molecules forming, rather. For 1 mole of these bonding, it's negative 436 kilojoules per mole, which is not a trivial amount. So per single bond, yes, it's tiny. Per mole, it's a respectable amount. So other concepts here. More overlap is possible when the orbitals are aligned along the same axis. So therefore, the bond is stronger. In this image, we see 2p orbitals. In picture A, they are aligned with each other and they overlap a decent amount. In picture B, they're overlapping at an angle, and so they don't overlap as much. Well, what else can we say about valence bond theory? Sigma bonds, given by lowercase Greek letter sigma, are made by overlapping two orbitals along the same axis, the bonding axis. Picture A is the overlap of two s orbitals. Picture B is the overlap of an s and a p orbital. And picture C is the overlap of two p orbitals, end to end. Note how the overlapping portions are all the same color. This is not accidental. Let's look at the next slide, which talks about pi orbitals, and see if we can find the same thing. Pi bonds, given by lowercase Greek pi, are made with two p orbitals that overlap with a node between the top and the bottom portions of the bond. Recall that a node is a place where electrons are not present. The node is a plane going across the axis between the two nuclei, the bonding axis. The electrons are being described by probability here, so we're still looking at two orbitals overlapping, but they're jumping from one side to the next and not touching the node in the middle. It's like jumping over a gap, suddenly appearing on the other side. Quantum mechanics is weird. Now, I mentioned that we should look at the overlapping colors, and again, we can see that the red overlaps with the red and the blue overlaps with the blue. This is not an accident. Red and blue are ways of representing the positive and negative lobes. Wait, what? Aren't they both representing electrons, which are in fact negative? Yes. Yes, they are. We're actually referring to the solution to the probability function. One side is the positive solution and one side is the negative solution to the function. When we square them, they're both positive. And that is what we show when we're showing electron density, but we color code them based on not being squared. When we orient these things in space, we must align the positive solution with the positive solution and the negative solution with the negative solution, or we've changed the frame of reference when making the bond. And that does not work out mathematically. So when you see representations of these, you will see overlapping colors, and it's referring to different solutions to the probability function, positive versus negative, not positive charge versus negative charge. Okay, moving on. All single bonds are sigma bonds. Double bonds contain one sigma bond and one pi bond, and triple bonds contain one sigma bond and two pi bonds. The reason for the node is made clearer when we add this tidbit of information. If you already have electron density along the bond axis from a sigma bond, the pi bond electrons cannot occupy the same space at the same time, so you get a pi bond instead. You can make a pi bond along two Cartesian planes you haven't already used. So if the bond axis is aligned along the x, you can overlap the p orbitals along the y and z axes, thus a triple bond, right? Because we have one along the x, one along the y, which is a pi bond, one along the z, which is a pi bond. It all makes sense. To summarize, valence bond theory explains the behavior of electrons in shared orbitals, otherwise known as covalent bonds. An orbital of one atom overlaps with the orbital of another. That's a basic assumption of this theory. Single electrons in each orbital combine to form an electron pair. More overlap is possible if they align along the same axis. If we put two s orbitals together, or an s and a p orbital, or two b orbitals aligned along the same bond axis, we call it a sigma bond, given by lowercase Greek sigma. If we have two p orbitals aligned perpendicularly to the bond axis, they're called pi bonds, given by lowercase Greek pi.